Right. So I've haven't really been following the Discord chat. So after this session, I'll try to catch back up. It's been a busy few weeks. But anyway, we'll get going, I guess, in just a minute here. So last week was an off week. So last time was 2 weeks ago, and we sort of, I guess, began the GKR protocol, but did not get to see a complete description of it. So that's what we'll do today. And then after that, I guess we have some options as to what to cover next. So I'll maybe put some thought into that also later today. So this is taking us to the end of chapter 4. So chapter 4 covers the sum check protocol and like a bunch of things you can do with it, with the GKR protocol being a major highlight. And so things we could cover after that. So we could follow the book, which I think covers the Fiat Shamir transformation next, which I sort of remember doing an unplanned coverage of that transformation at some point, but definitely worth kind of doing a more planned session on it. So that's one thing we could do next. I could cover. I think I tried covering Spartan before we saw SumCheck. Spartan is a SumCheck based snark for R1CS. So snark based on SumCheck for R1CS. I could cover that again, and possibly people would prefer me not to do R1CS, but rather some people prefer arithmetic circuits. Just as if you're not comfortable with R1CS already, arithmetic circuits can feel more natural. And so I could cover sort of a predecessor of Spartan called Clover, so that I'm not literally repeating stuff I covered previously during this run of the reading group, but nonetheless recounting the same ideas from when I did try to cover Spartan before we saw SumCheck. Or finally, we could start talking about if we sort of, are comfortable with Fiat Shamir, because I talked about it at some point, and kind of comfortable with Clover / Spartan, because I also talked about that at some point. We could jump ahead to, I guess, chapter 9, I think, which is sort of the chapter title is IOPs. But really what I would cover first is something called constant round polynomial IOPs, which is sort of the same kinds of protocols we've been seeing, but not based on SumCheck. So no more SumCheck. It would be based on univariate polynomials rather than multivariate polynomials in SumCheck. So kind of, how can you get the snarks we've been discussing for the last few weeks now without SumCheck, and like what is the benefits and the downsides of that? So these are the three things we could move to next. It might be useful to get some feedback if anyone has preferences. So maybe I will follow up after today's session with asking for some votes or something about what to talk about next. But these are so these things would be like the Marlin polynomial IOP. So you can basically choose Fiat Shamir, Clover / Spartan, or Marlin as our next topic. and then we'll go from there. Probably after we get through, these three things, and again, maybe the first two we've kind of already discussed, and perhaps we don't want to revisit. Kind of take your thoughts into account. Once we get through these, Marlin anyway, we could then move on to polynomial commitments, which is a whole long topic that will take quite some time. As well as zero knowledge, which we haven't really talked about much yet. So polynomial commitments, which are built out of something called Sigma protocols. All of this is wrapped in with zero knowledge. So those will be the remaining topics. Anyway, okay. So that is what we're talking about today, and follow. Yeah. Any questions or thoughts?
So I just wanted to say I would love to help maybe put together a survey or something to see what people want to study next. So maybe you and I can think about that afterwards or later this week. But I'd love to help figure out what we want to do next. And it looks like we might have a question from Suki, who I just invited to the stage.
Great. Sounds great.
Hello, Professor. Hope you're doing great. I think last time we wanted to just see that how the MLE of each layer, this is with respect to GKR, MLE of each layer is constituting to form an MLE for the input layer. This is the piece that was missing for me. I don't know whether it was just me. If you could, wherever in the course of today's lecture it suits you, if you could just give an intuition about it, it would be great.
Great. Yeah. Okay. So I guess that is largely the main, goal of today. I think that kind of goes hand in hand with just understanding how the GKR protocol works in detail. Sort of once you understand, how the MLEs of the interior gates relate to the MLE of the input, the GKR protocol kind of just falls out of that relationship. Let's make sure that becomes clear, and I'll try to highlight that and ask the question again if I don't make things perfectly clear without extra prompting.
Thank you, sir.
Great. Cool. Any other questions? Okay. All right, so yeah, let me quickly review terminology that we need to describe the protocol. And I guess one more comment before we dive in. I'm going to describe the protocol kind of in full generality. So maybe I'll write this down. So we're going to see it in full generality. Okay. But then, and I'll sort of hand wave about how to make sure the prover's really fast in the fully general case. But then I will kind of recover the protocol tailored to a special case of grand product circuit. And life gets just much more simple in this case. And the stuff that I'm going to hand wave in the fully general case, I will not need to hand wave at all because they'll just kind of be trivial in the special case of grand products. And I think this special case is sort of particularly important in practice, kind of at the heart of kind of the SNARK techniques that I think are ultimately going to be key to the fastest provers and stuff like that. So I'm covering this special case, in full for two reasons. One is it's nice and extra clean, and two is it's just an important special case. So just a heads up, if there's anything you don't like about the fully general case, hang in there till the special case, and you might like it a little bit more. Okay, so in the GKR protocol, sort of the prover and verifier sort of, both know or agree upon an input X in field to the N, and a circuit, and let's say a layered fan into, and I'll remind you what these terms mean in a moment, arithmetic circuit C over the field, where X is an input to C. Okay. Okay, so what does that mean, like in a picture as an example? So with an arithmetic circuit, so before I remind you what an arithmetic circuit is. So the picture is like we're feeding X into this big circuit C, and there could be one or several outputs. Maybe let me call it the claimed output. So the prover is going to send some claim for the outputs. Let's say there are M of those. And so the point of the GKR protocol is it's an interactive proof, which I'll abbreviate IP, for the claim that if you evaluate the circuit C on input X, the outputs produced equal Y. Okay, so like X is the input to the circuit, C is the circuit, Y are the claimed outputs. Okay, and so what is a layered arithmetic circuit of Fanon 2? So it consists of addition gates and multiplication gates. So just as a little example, let's look at this circuit here. So let's say it has, I don't know, 4 inputs. And let's say what we're going to do is just like square each input and sum up the results. Okay, so that circuit would look like this. Oops, these are So every input is sort of fed twice into a multiplication gate that has the effect of squaring each input, right? So if when you evaluate this circuit on these inputs, right, like this gate evaluates to x1 squared, this gate evaluates to x2 squared, x3 squared, x4 squared. So this red text is just like the value of the gate when the circuit is evaluated on this particular input. And then we have this binary tree of addition gates that just sums up the values of the multiplication gates. So the value of this addition gate is winds up being x1 squared plus x2 squared, and this one winds up being x3 squared plus x4 squared. Since its neighbors are these two multiplication gates, and then finally the output gate winds up with value the sum of these two gates. So that's x1 squared plus x2 squared plus x3 squared plus x4 squared. So this is a little simple kind of toy example of a circuit. And what Fanon 2 means is that every single gate in the circuit, other than the inputs, of course, have exactly 2 in neighbors, or at most 2 in neighbors. So two arrows feeding into them, like this arrow and this arrow are the 2 in neighbors for this addition gate here. And then layered means that you can break the gates of the circuit into layers, so that like all of the inputs to a gate at layer I live in layer I-1 or I+1, depending on how you want to number the layers. So this is an example of a layered circuit of Fanon 2 over whatever field you're working over. Okay, and so the GKR protocol, when your circuit, so this circuit, has, I refer to the inputs as gates too. Many people do not call the inputs gates. But it's just a convention thing. It doesn't really matter. So according to my terminology, this circuit has 4 plus 4, so that's 8. 10, this has 11 gates. 4 input gates. 4 gates at this layer, 2 gates at this layer, 1 gate at this layer. You add that up, you get 11. And so when the input size is 4. And the circuit size, as a whole is like not all that much bigger than 4. There's not like a huge point to using the GKR protocol, right? Because the verifier time in the GKR protocol is order input size. And more specifically, okay, so let me write this out more. So it's order input size plus circuit depth. So this little d is the number of layers. okay, times like log circuit width, but let's just call a crude upper bound on the circuit width is the circuit size. The size is like the sum of the width of all the layers. So yeah, and typically, unless the depth is really big, this d log circuit size term tends to be much smaller than this order n term. And so, as long as the depth isn't big, the verifier time in the GKR protocol can actually be as low as something like 2n field operations, roughly something like that. Maybe even it can be as little as about n field multiplications. So maybe even about n field multiplications. And so, roughly speaking, the verifier is like just reading the input. Okay, so if the circuit is like much bigger than the input, then the verifier is saving a lot of time here by using the prover. Okay, but in this little teeny example, the input is like a third of the circuit, and so the verifier is not saving very much time compared to just ignoring the prover and evaluating the circuit on its own, right? So just keep that in mind. In SNARK applications, though, like often the input is committed, and so the verifier doesn't even have to read it. And in that situation, this order n term goes away, and then there can be a major benefit to applying the GKR protocol to a circuit like this. Even if the circuit is not that much bigger than just the size of the input, just because the verifier doesn't even have to spend the time to read the input. So for today, we're going to just assume that this is sort of coming from V reading the input. In SNARK applications, the input to the circuit will be committed, and so the verifier might not even have to do that. But yeah, anyway, for today, let's imagine the verifier does read the whole input.
Question. Am I understanding that like that whole reading of the input in some cases is actually like the main computational cost, and so that's why you're making that distinction of like in Snark applications it's already committed, so we don't even have to do that.
Yeah, exactly. So for the verifier, reading the input is the main cost. Yeah, and so in Snark, and so everything you said is correct. Yeah, and if
and
those,
then
yeah, go ahead.
We had a question, Skanov, is so I see that the x's are clearly like a vector. We can have many values that make up the x input. For the output y, is that a single value, or can it also be like a tuple, like a multi-valued vector?
Yeah, it can be a multi-valued vector. The way I'll describe the GKR protocol, I'll handle it's just very easy and natural to describe it when there is a vector of outputs.
Could you possibly draw a diagram of that just so that we have that visual to better understand this thing?
Yeah, great. Sure. Let's just switch this example. So it has, let's say, two outputs. Let me try to clean this. Keep losing my eraser for some reason. Is that not the eraser? What's going on?
It is. Are you using an Apple Pencil?
I am, yes.
So it has a weird behavior, and I actually think I saw you got a pop up about it earlier about being enabled or disabled. Basically, there's like a flat side on the pencil, and if you tap it twice, it alternates between your eraser and pencil, which of course I do all the time on accident. So that.
Okay, all right. See if I can. All right, did that fix it or not? It did. Whatever. I'll fix it after today. I feel like I'm going to spend too long trying to. Thanks for telling me, though. I never would have figured that out. Even with the suggestion, I still am struggling. So, great. Okay, so yeah, let's just give this circle, this circuit, two outputs. Let's see, what would that be? We can. Well, okay, I'll do a new one. So x1, x2, x3, x4. Let's say times here, plus here. Okay, and let's say we got an addition gate that's going to add these two, and a times gate that's going to multiply these two. All right, so that this will be our example circuit moving forward for today. Really small, simple circuit, kind of dumb, but yeah. So it's got 4 inputs and 2 outputs. Okay. Other questions?
Nope.
All right. Okay. So, last time I covered the notation that for every layer of the circuit, we were going to consider like a gate value function for each layer I of the circuit. I don't have the book in front of me, so I think I normally number the layers in the book like this would be layer 0, the output layer, and then we count up from there. So in this case, the input layer would be layer 2. And this circuit has depth 2, so this 2 is the same as little d for depth. And so each layer we consider a value function. So let's call this value function maybe w sub I. And what this function will do is it will take as input a binary label of a gate at layer I and spit out the value of that gate. When the circuit is evaluated, on this input X that both the prover and verifier have agreed upon. Okay, so just to cover this specific example here, let's say the input values are 1, 3, 0, 2. So this multiplication gate winds up having value 1 times 3, which is 3. And this addition gate is 2 plus 0, which is 2. And then this output addition gate here is 3 plus 2, which is 5. And this is 3 times 2, which is 6. So for this example, W0 maps 0 to 5 and 1 to 6. Right, because there are 2 gates at this level, this output level, and I'm just assigning the first gate label 0 and the second gate label 1. So this is the valuation function for layer 0. For layer 1, we have W1 of 0 is 3, and W1 of 1 is 2. And then for layer 2, we have. So this takes 2-bit labels because there's 4 gates at the input level. So you need 2 bits to index 4 gates. Similarly, you need 3 bits to index 8 gates and 4 bits to index 15 gates and so forth. So W2 of 0, 0 is 1. W2 of 0, 1 is 3. W2 of 1, 0 is 0. And W2 of 1, 1 is 2. So that's the gate value function stuff. Okay, for this, example. And then finally, for each layer, this is notation I didn't quite introduce last time until I was, rushing and sketching things at the very end. So again, for each layer I, we'll have 2 functions called addi and multi. Okay, and these take as input 3 gate labels, but so let's say A, B, and C. And so this is A is a gate label for a gate at layer I. And B and C are gate labels for gates at layer I plus 1. Okay, and so add I of A, B, C is 1 if B and C are the in neighbors of gate A. At layer I, and A is an addition gate. And 0 otherwise, right? So what this add I function is doing is it's like an indicator function. Like it's saying, is gate A an addition gate? That's computing the sum of gates B and C. If so, output 1. If not, output 0. Okay. And similarly, malt is like the same thing. So I'll just write it, in pink here. The only thing that changes is add turns to multiplication gate. So, if we're in pink, everything's the same except this word add goes to malt. Good. So like just in this example, coming back to the example real fast, I guess I'll write in pink, so for layer 0, so like add 0 of 0, so this would be gate A, comma 0, that's gate B, comma 1, that's gate C, would be 1. That's because the in neighbors of gate 0 at layer 0, the first in neighbor is gate 0 at layer 1, and the second in neighbor is gate 1 at layer 1. Okay. But like, if I add 0, if I change like anything here, if this 0 turns to a 1, or this 0 turns to a 1, or this 1 turns to a 0, it will spit out 0. So add 0 of anything else in the it will equal 0, right? Because this gate's a multiplication gate, so add is definitely going to evaluate to 0 if I were to feed 1 in for gate A rather than 0. And gate 0 is an addition gate, but its in neighbors are gates 0 and 1. And so if I don't feed in 0 and 1 for the second two things, add will kill the triple. I just as one more quick example, let's do layer 1, just because the in neighbors of layer 1 have 2-bit labels rather than 1-bit labels, since layer 2 has 4 gates rather than 2 bits. So like add 1 of 1, so that's like gate A, comma what is this 1 0, so that's gate B label, and 1 1 would be, that's gate C's label, would be 1, again because this addition gate here, its in neighbors have label 1 0 and 1 1 at the preceding layer. But like if I were to make any small changes here, like if I change this 1 to a 0, then this would spit out 0, right? Because the 0th gate at layer 1 is a multiplication gate, not an addition gate. In addition to the fact that its in neighbors are not 1 0 and 1 1. So conceptually, these functions addi and multi, together they just capture the what we call the wiring of the circuit. That is, which gates are connected to which other gates. Also, is each gate an addition gate or a multiplication gate? So this is like, these addi and multi functions are how the GKR protocol sort of understands, internally within the protocol what circuit we're dealing with, right? Like until I brought in these addi and multi functions, like we talked about values of gates, but we just had nothing capturing the wires of the circuit, right? Like, these addi and multi functions are exactly how the protocol understands or represents, what operations the gates in the circuit are actually doing. Okay. So that's all the notation we need. So let me pause here, see if there are any questions.
There was one. There's another. So the first from Skona says, "What would change if we collapse the binary label or index to just a single number?"
Great. So you can do that. So right now we're sort of assigning each gate a binary label and mapping gate labels to values and things like that. You could instead index each gate with a number between 0 and like size of that gate's layer, rather than with bits. Then you couldn't use the sum check protocol, basically. So what I'm just about to get to is, for every one of these functions we just introduced, right? Their domain is the hyper 0, 1 to the, 0, 1 to the k for some k, right? They're dealing with binary inputs. And so it makes sense to talk about their multilinear extensions. So WI, ADI, and multi, they're each dealing with binary inputs, 0, 1 valued inputs. So you can talk about their multilinear extensions. If they each dealt with, if gate labels were one number each instead of zeros and ones, you couldn't have multilinear extensions of these functions. And so like WI in that case would, like, its natural extension would be a univariate polynomial. And the degree of that polynomial would be the width of that layer. And that would be very high degree. And so in the resulting interactive proof, you just would have like very big proofs that are useless as far as the verifier is concerned. The proofs are so big. And so when snarks use univariate polynomials, the proofs are not necessarily big, but what then happens in the snark is the prover commits to a lot of data. And so you can wind up with very small proofs. You can use univariate polynomials rather than multilinear in the snark and wind up with very small proofs, but the prover winds up committing to a lot more data, and that results in a slow prover oftentimes. So the benefit here of the binary labels everywhere is you can use multilinear extensions, which keeps the proof size short, even without bringing in the commitment schemes, right? Because the GKR protocol is an interactive proof. There's no commitments, right? As long as if the verifier knows the input X, nothing has to get committed whatsoever. Okay, did that answer the question?
Yeah. And then I think we had someone else who'd popped on stage to ask a question as well. Go ahead.
Go ahead.
Cosmo? Yeah, you're not speaking. Yeah, I think we just move on.
Okay, sounds good. Feel free to try again if something technical happened.
Cool.
Okay. Yeah. So that's these are the functions. The definition of the various functions that the GKR protocol needs. And so yeah, like again. So WI has domain like So let WI tilde be the multilinear extension polynomial of WI. Remember the domain of WI is 0, 1 to like the log number of gates at layer I of the circuit. And so, any function with this domain 0, 1 to the blah has a unique multilinear extension polynomial. So the number of variables is, so the number of variables that WI tilde is defined over is what I just wrote over here, log number of gates at layer I, also known as the width of layer I. So just as and similarly, like ADI tilde, multi tilde will denote the multilinear extensions of ADI and multi. So MLEs, multilinear extensions of ADI and multi. So just, bringing this back to the example here. So W1 twiddle has a single variable as input. So I guess I'll call that X1. And that will just be 3 times 1 minus X1 plus 2 times X1, right? So I just did like multilinear Lagrange interpolation, right here on the fly. You can check that this thing is multilinear in X1. It's in fact, because X1 is just one variable, it's literally linear. It's a line, and it maps 0 to 3 and 1 to 2. So it's, as a result, it's the unique multilinear polynomial that has the same evaluations as W1 does anywhere W1 is defined. And yeah, just one more example, like so W2 here, twiddle, is a two-variate polynomial, and just doing Lagrange interpolation on the fly, it would be 1 times 1 minus X1 times 1 minus X2 plus 3 times 1 minus x1 times x2 plus 0 times, whatever, because it's 0 times anything, is 0, plus 2 times x1 times x2. Right. And you can check, easily. This is multilinear. It has degree 1 in each of the two variables, x1 and x2. And indeed, it maps 0, 0 to 1, 0, 1 to 3, 1, 0 to 0, and 1, 1 to 2. So, yeah. So that's wi twiddle, addi twiddle, multi-twiddle. Okay, good. So now here's the key fact. So what I want to do, and this is hopefully about to answer the question that I was asked at the very start of today. How do the multilinear extensions of the interior gate values relate to the multilinear extension of the input? So what I'm about to do is I'm about to express wi twiddle of x in a nice way. So I'm about to just give an expression for wi twiddle of x. That expression is going to let us start using the sum check protocol. But let's just write out the expression. Remember, this x, it's the number of variables. So x here is like x1 up to x. Let me just call it k, where k is log number of gates at layer I. And so I just want to emphasize x is like not one variable; it's several variables. So wi twiddle of x can be written as follows. So it's the sum over bc in 0, 1 to the log number of gates at layer I plus 1. So think of these as labels of gates at B and C are binary labels of gates at layer I plus 1. Okay. Of something. So let me write out what the something is. I'm not going to try to squeeze it. Can I move? Sorry, this scroll bar got moved and now it's in my way. There we go. Okay, so yeah, I didn't want to try to squeeze this expression just in that sum. So let me write it down here. So yeah, here it is. So we have addi twiddle of x comma b comma c times wi plus 1 twiddle of b plus wi plus 1 twiddle of c plus multi-twiddle of x comma b comma c times wi plus 1 twiddle of b times wi plus 1 twiddle of c. Okay, so maybe I can, and maybe this actually fits up there. Maybe I can move it. Let's see. All right, let me just move the sum down. Actually, maybe that's the way to go. Oops. Let's take the sum. Almost legible, not quite legible. All right. Let me just rewrite it. Apologies. All right. So sum over BC in 0, 1 to the log number of gates at layer I plus 1. All right. So that this is the key. This is the key claim, the key fact. All right. And so whenever we see a claim like this, I say, some multilinear polynomial equals some other thing, right? Like how do we check that claim is true? You always want to check two things. So you check the right-hand side. So this big sum is multilinear in X. And then you check that if X is 0, 1 valued, 0, 1, if X is in log 0, 1 to the number of gates at layer I, then the left-hand side of X equals the right-hand side evaluated at X. So if you check these two things, then the right-hand side must actually equal the left-hand side as polynomials, because there's, if I give you any input-output, behavior over the Boolean hypercube, there's always a unique multilinear polynomial with that behavior. So if the right-hand side is a multilinear polynomial with that behavior, and the left-hand side is also a multilinear polynomial with that behavior, then they must be the same polynomial. Okay, so let's do the two checks. So the first check is straightforward, right? Like add-I-twiddle and multi-twiddle are fed X. And X isn't fed to anything else on the right-hand side. And add-I-twiddle and multi-twiddle are multilinear. And they're not multiplied together, right? So like, this thing is multilinear in X, and this thing is multilinear in X, and so these things are like summed together, and you sum multilinear things together, and sums don't affect the degree, so everything's still multilinear. So great. The right hand, the right hand side is indeed multilinear in X. Okay, and then checking, next we want to check that for all Boolean X, the right hand side and left hand side spit out the same value. Okay, and so what does the left hand side spit out for Boolean X? It just spits out, so if X is Boolean, so X is in 0, 1 to the log number of gates at layer I, then Wi twiddle of X is just Wi of X, which was defined to be the gate value of gate X at layer I. Okay, so what we want to show is that the right-hand side, this big sum, indeed, if X is a gate label for layer I, this big sum indeed spits out the value of gate X at layer I. Okay, and I just realized I had used X for the inputs of the circuit, and now I'm using X as, like a gate at layer I. So apologies for kind of overloading X, but hopefully it hasn't been too confusing so far. And so what's going on here is like, if gate X is an addition gate, if gate X at layer I is an addition gate, okay, then when you feed X into it, it's gonna spit out 0 no matter what B and C are. Yeah. And add I will spit out 0 for every term of the sum except the term where B and C are the in neighbors of gate X, because that's how we defined add I.
I think an easy way to look at what's happening here is that like we're adding a ton of terms, but only one of them is going to be non-zero, right?
Yes, because of the add I and multi.
Mm-hmm. And that term that is non-zero is exactly what we want, because if it was a multiplication gate, then we've multiplied the two previous values. And if it was an addition gate, we've added the two previous values sort of on the right side of your sum. But yeah, it seems clear.
Yeah, that's it. Good. So I won't belabor the point. That's exactly right.
Cool. We have several questions, so I'm going to try to go through them quickly. The first is why does V already know the input? You've said that a few times. I wasn't really sure what you meant by that, but it sounds like, yeah, in some cases V has to read the whole input. Sometimes it doesn't. What affects that?
Yeah, so that's just application dependent. So like the GKR protocol as originally described in the 2008 paper that introduced it, just considered the situation where the verifier knew the input X, not this X, knew the input to the circuit. Okay, and yeah, so like if you just want to talk about the GKR protocol, that is the situation that the GKR paper considered. Okay, in SNARK applications, typically this input X will actually to the circuit will actually have already been committed, and in that context, the GKR verifier actually doesn't really need to know, doesn't need to read or know X. So as we're going to see in the end, the GKR verifier doesn't really need to know all of X. What it needs to know is it needs to evaluate the multilinear extension of the input. Again, not this X. This is the multilinear extension.
Essentially, like the verifier is able to confirm that like evaluation at X equals Y without ever knowing X.
Yeah. In some applications, the verifier just knows X. In other applications, X was committed. and the only information the verifier ultimately will need to know about the committed input will ultimately be able to be pulled out of the commitment. So like the way that the input winds up getting committed in SNARK design is people use what's called a polynomial commitment scheme specifically because what is a polynomial?
And when we're committing the polynomial, we are not actually giving them the polynomial. We are just locking ourselves into the choice of polynomial.
Exactly.
But that's why when we say we've already committed to the polynomial, that doesn't mean that the verifier is going to read it because they actually don't even have it.
Exactly.
Cool.
Yeah.
Then we had one more question. And sorry, did you have more to say there?
I was just going to mention, like in SNARK applications, often this input to the circuit is sort of like a entire trace or transcript. It's like everything that happened while the prover ran the computation it's claiming it ran correctly. And so often in the SNARK, this input to the circuit is huge. Like there's no way for the verifier to, read the whole input, even if the prover sent it. It's just too big. And that's why in SNARK land, the input to the circuit will have been committed with this polynomial commitment scheme because it's so big.
Okay.
Yeah.
Can we separate the W extension for each layer, meaning that every layer has its own extension?
So that is what's happening here in the GKR protocol. Okay. So, and this is very unique to the GKR protocol. So if you look at, Spartan, Clover, and any of like the SNARK space and univariate polynomials, they tend to treat the entire circuit as one monolithic object. And so they'll kind of treat all the gate values in the circuit as a single vector and commit to that vector or whatever, define one function capturing all the gates in the circuit. The GKR protocol does not, it treats each layer of the circuit as a separate function, as a separate vector. So that's exactly what's happening here. And the reason it does that is sort of as compared to all the other approaches or techniques is to avoid committing to the values of the of the internal gates of the circuit. So somehow, if you commit to everything all at once, it's then kind of okay to treat the whole circuit as one monolithic object. But if you really don't want to commit to all of those internal gate values, you really do have to kind of treat each layer separately. And so that's exactly kind of the trade-off that's happening here. GKR kind of proves each layer one layer at a time, and so the proofs can get a little bit big if there's a lot of layers. That's the downside. On the plus side, like the prover only commits to the either only the input might be committed, and possibly even that might not be commit. If the verifier just knows the whole input, it doesn't need, and nothing needs to be committed. Does that make sense?
I didn't follow what you were saying about the other scenario where you have to commit everything in the computation. Why do you have to commit all of it, whereas here you don't?
So I guess the way I put it is we're about to see exactly how the GKR protocol goes one layer at a time. We're almost there. We haven't quite gotten there. We're literally cool. Like that. And so maybe when we see that, things will be clearer. You'll see, why going one layer at a time works, and that should also explain why trying to handle all the layers all at once doesn't work unless they were all committed in advance.
Cool. Go ahead.
Okay.
I had a quick question, Professor. So, keeping aside this application layer compilation via some commitment scheme and whatnot, I'm not sure why we are emphasizing on verifier not knowing the instance, because this is an information theoretic proof system, and given that it is not strong verifier, so the verifier by definition knows the instance.
Right.
Isn't that the way to, am I getting something incorrect here?
No, I think you're getting it correct. So I think I'm confusing things by bringing in the possibility of the input to the circuit being committed, and that's just making things confusing. The reason I am doing that at the risk of creating confusion is because I think most people are here in the study group due to interest in snarks. And in those snark applications, the input does tend to be committed, and the circuit tends to be linear. The circuit size tends to be linear in the size of the input. And in that context, were the circuit not to be committed, were the input not to be committed, there wouldn't be much point to the protocol at all. So I think the cleanest and correct way to understand the GKR protocol as a standalone protocol is to just consider the situation that the verifier knows the input to the circuit, right? Then there's no commitments, there's no cryptography, it's just an interactive proof. It's information theoretically secure, unless you fiat shamir it. I just want people to keep in mind that, like in snark applications, often the input to the circuit is committed. The circuit has size linear in the size of the input, and so nothing would really make much sense to use unless the input were committed. Does that clear things up at all, or did that?
Yes, sir. So now that you say this, I just had one curious question. You can choose to ignore it. Is that is there any follow up on GKR just on an interactive proof system note, having to add the property of strong verifier onto the GKR protocol, meaning the verifier not knowing X?
So what does strong verifier mean?
It means that the prover would be knowing the instance and the witness. The verifier would not be knowing the instance. So, yeah, if it kills the time, you can choose to ignore it.
I guess I'll just say, if I can give you any, interactive, run of the GKR protocol, right?
Mm-hmm.
And then, the prover and verifier talk, and they work their way from the claimed output to a claim about the input, and they're done. The protocol's over, right? At this point in time, if the prover now got to choose the input because the verifier doesn't know the input, it's very easy for the prover to choose some input where that does not actually produce the claimed outputs yet passes the checks, right? Another way to say it is at the very end of the protocol, the prover winds up making a claim that this X is the input to the circuit. So the prover winds up making the claim that the multilinear extension of X at some random point equals some value Z. Okay. Now, if the verifier knows X, it can just compute this evaluation on its own and confirm or refute the claim itself. But if only the prover knows X, at this point, it'd be very easy to just find a different X with the same call it X prime, so that the multilinear extension of X prime also evaluated at R equals the same thing. Yet, so this is easy to find at this point. C of X prime does not equal the claimed outputs.
So am I getting it right? So soundness of GKR is not straightforward if I'm trying to give the property of honest verifiers zero knowledge. Meaning the verifier must know X is what you're trying to say.
Either the verifier has to know X or X has to be pre-committed. So the key point is it's absolutely not okay for the prover to be able to choose X after the protocol has been run.
Yes, sir.
Yeah, that's the key, and that's why the snarks would commit the input X in advance to prevent the ability of the adversary from choosing X in a way that depends on what happens within the GKR protocol. Did that make sense?
Yes, sir. Thank you.
Okay, great. Okay, more questions?
Yeah, there's one more. I'm going to read it from chat. What happens if, for example, we check layer by layer, similar to a Merkle tree, until the last layer and use a random value from the finite field? In that case, we would apply the Schwartz-Appel lemma to find the final polynomial of the last layer. And if I'm correct, we would still maintain the soundness property.
So I'm not sure I fully understand the proposal or suggestion. Let's take so feel free to clarify the question, but let's also see if because I'm fairly close to describing the whole protocol at this point. Let's see if the description of the protocol somehow clarifies things, by itself. So yeah, just feel free to ask the question clarified a little bit in a few minutes.
Cool.
Okay, so here's the key fact, right? We expressed the multilinear extension of the gate values at layer I in terms of some big sum, where the sum involved the multilinear extension of gate values at layer I plus 1. So this is like one layer closer to the inputs. Gate I is, I layers from the output. And, so as I increases, you get closer and closer to the inputs until you hit layer D, the highest layer, which literally is the input layer. Okay, so what we're going to do, so here's how the protocol works. I'm going to try to, all right, let me erase the proof so I can keep the fact as visible as possible as I describe the protocol. All right, this eraser thing is terrible, but let me just try to do it all at once without picking the pen up. All right, okay, that didn't, almost made it. Okay, good enough. All right, so the way the protocol starts is the prover sends the claimed outputs Y. Okay, and what the so let Y twiddle be the multilinear extension polynomial of the claimed outputs of Y. Remember, like what we're doing here is we're interpreting the claimed output vector. We should be used to this by now. We interpret it like not really as a vector, but instead as a function, mapping binary gate labels, binary labels of output gates to the claimed value of that gate. Okay, and once we interpret, Y as a function whose domain is binary gate labels, it makes sense to talk about as multilinear extension polynomial. Okay, so what the verifier does is it picks an R0 in field to the log number of outputs, and computes Y twiddle of R0. Which it can do with multilinear Lagrange interpolation in time linear in the number of outputs. Great. So that's how the protocol starts. And that's why, remember I was asked, can there be multiple outputs? And I said yes. And in fact, I think it's most natural to describe the protocol when there are multiple outputs. And this is what I was referring to. So like what the verifier does with the outputs is it literally just like evaluates the multilinear extension at a random point. Okay, so that's how the claimed outputs are processed. Okay, and so by the short Zippel lemma, right? It is safe for the verifier to believe that the claimed outputs are equal to the real outputs, so that C of X equals Y. If the verifier is convinced that okay, so let me call the real outputs, let me call those let's come up with a letter here, I don't know, S. Not a great letter, but let's stick with it. So if the verifier is convinced that S twiddle of R0 equals Y twiddle of R0, right? So what's going on, like this, hopefully we're getting comfortable with this kind of statement, right? So like what this statement's a little informal. It's safe for the verifier to believe the claimed outputs are the real outputs if this equality holds. Like what I'm really saying is if the claimed outputs Y are not equal to the real outputs S, then with overwhelming probability over the choice of R0, it will not be the case that Y twiddle of R0 equals S twiddle of R0, because Y twiddle and S twiddle will be different multilinear polynomials. And so, the probability they agree at a randomly chosen point is minimal, is like, degree over field size, which is tiny or something. Okay. So the point is, like at this stage of the protocol, the prover made a claim about all of these outputs in Y. And the verifiers kind of reduced that claim to a single evaluation of the multilinear extension of those outputs. Okay, and we're going to see this over and over again now throughout the protocol, where like at each layer of the circuit, the verifier will kind of start with a claim about a single evaluation of the multilinear extension for that layer, and turn that claim into like an equivalent claim, meaning this kind of safety thing. It's okay to believe one claim if you believe the other claim, to a claim about the preceding layer. Okay, so this is how that's done. Feel free to interrupt me with questions. So so by this fact, this fact says, remember, I guess I shouldn't, this S twiddle, like these real outputs, the real outputs are the same as W0, W0, like the 0th layer of the circuit is the output layer. And I define W0 to be like the actual gate values at the output layer. So I probably shouldn't have introduced S. I should have just said W0. So actually, let me actually change that real quickly. Sorry about that. So the verifier, at this point wants to compute what actually is W0 twiddle of R0, right? This is what the verifier needs to figure out at this point. Okay, so by the fact, the fact says, hey, W0 twiddle of R0 is the same as the sum over BC in 0, 1 to the log number of gates at layer 1 of this somewhat gross expression. I'll just write it out real quickly. Add twiddle 0 of R0 comma B comma C times W1 twiddle of B plus W1 twiddle of C plus malt twiddle 0 R0 B comma C times W1 twiddle of B times W1 twiddle of C. Great. So that's what the fact says. So as a result, what we do in the protocol is we apply sum check to compute this big sum. Great. Now here's where I wave my hands real quickly. So this sum is over pairs of gate labels, for layer 1. It turns out you can actually implement the sum check prover here, to compute, when you apply sum check to compute this big sum, you can actually implement the sum check prover. It runs in time, order like number of gates at layer 1. So you actually don't have to sum over pairs of gates. Roughly, why is that the case? It's because, for every gate B, for every gate A at layer 0, there's like a unique pair of gates B and C that cause, this sum not to just spit out 0. Since every gate A at layer 0 has 2 unique in neighbors B and C. So anyway, so that's where I'm waving my hands. But if I do manage to cover the grand product thing, like this sum winds up, not actually being over 2 gates B and C, and then it's sort of trivial. This sort of prover time claim I'm making. Anyway, so let's forget about sum check proving time here. Just one way or another, we apply the sum check protocol to compute this big sum, and at the end of the sum check protocol, the sum check verifier needs to evaluate the polynomial being summed at a random point. Okay, so so this means, at the end, the verifier needs to evaluate, this polynomial that's being summed at a random point. And so what that means, evaluate add 0 twiddle R0 comma the random point, which I'll call it R0 prime and R0 prime prime. This is like the sum check verifier randomness. So sum check randomness, the random values chosen over round by round over the course of sum check protocol. It needs to evaluate W1 twiddle of R0 prime and W1 twiddle of R0 prime prime, and it needs malt 0 twiddle of the same thing, R0 R0 prime R0 prime prime. Okay, so great. So that's this is the core of the GKR protocol, right? We had this nice expression for W0 twiddle as this big sum. We apply the sum check protocol to compute that big sum. At the end of the sum check protocol, the verifier has to evaluate the polynomial whose evaluations are being summed at a random point, and that involves these 4 evaluations here. Okay, now I will just assert to you that for many, many, many circuits, the verifier can get these evaluations of, add 0 twiddle, mod 0 twiddle on its own very quickly. So let me wave my hands there, just assert it. You will see for something like a binary tree multiplication gates, this doesn't even come up. Okay. So let me just say the verifier for many circuits on its own in log circuit size time, can compute these, add twiddle and mod twiddle evaluations. Okay, so if you just believe me about that, then here's what the verifier really is left with. So it's the prover started with a claim about W0 twiddle at one point, R0, and that has been turned into a claim about W1 twiddle at 2 points, R0 prime and R0 prime prime. Okay, and so what we'd really like is for the verifier to instead be left with the claim about W1 twiddle evaluated at 1 point, right? And that once we get to that, it's clear we've really made progress. So before I cover how we do that, let's just imagine for a second that the verifier didn't need W1 twiddle at both of these points, but rather just at one of the points, our W1 twiddle of R0 prime. Then we'd be great. Then we're done designing the protocol. Okay, so let just imagine this for a second, even though it's not true. So what we've done, the prover kind of started with a claim about W0 twiddle of R0, and that got turned into a claim about W1 twiddle of R0 prime, right? And so we had a claim about the output layer. We turned it into a completely analogous claim about one layer closer to the input. We can now do the exact same thing, right? And just to sketch what that is, we use the fact from before to write W1 twiddle of R0 prime as sum over gate labels for layer 2, log num gates, number of gates at layer 2 of, add 1 twiddle R0 prime BC times, I'm sure you're sick of me writing this out. W1 twiddle B plus this is 2, W2 twiddle C. This will be the last time I write it out. R0 prime BC times W2 twiddle of B times W2 twiddle C. So you apply sum check to this thing. To compute the big sum, at the end of sum check, the verifier needs, add 1 twiddle of, R0 prime, R1 prime, R1 prime prime, W2 twiddle of R1 prime, W2 twiddle of R1 prime prime, and the mult twiddle evaluation as well. Right. And, I'm going to say the same things as before, for many, many, many circuits, the verifier can get the add twiddle, mult twiddle evaluation very quickly on its own. And so now the verifier is really just left with 2 evaluations it needs of W2 twiddle. And if we just pretend for a minute that it really only needed one of those 2 evaluations, great. We have now reduced the claim about W1 twiddle of R0 prime to a claim about W2 twiddle of some random value R1 prime. And then we do the same thing again. To reduce the claim about W2 twiddle at a point to a claim about W3 twiddle at a point. And we just keep going until eventually we get to the input layer, WD, and the prover winds up making a claim about WD twiddle evaluated at some random point. And this claim, as I said before, the verifier, can compute this directly because it knows the input with multilinear Lagrange interpolation in linear in the input size time. Okay, so that is the GKR protocol, up to the one fudging thing about how really there's 2 evaluations of WI twiddle the verifier needs at each layer. And right now I'm saying, well, ignore that and act like there's only one evaluation of that verifier needs for each layer. So that's it. So yeah. So pictorially, we have this layered circuit. Here's the input to the circuit X, and then we have like some layer below that. So this is the input is layer D. This would be layer D minus one. Layer D minus two. Down to the output layer, which is layer 0. Right. It's just regurgitating the protocol again. The prover sends the claimed outputs. The verifier evaluates the multilinear extension of the claimed outputs at a random point. By short zipple, all the outputs are okay, kind of up to some small soundness error, if and only if like a random evaluation of that multilinear extension is valid. So in that way, we have a single evaluation of W0 twiddle that we need. Apply some check once for the output layer. That turns it into a claim about W1 twiddle of some random point. The apply some check again. That turns a claim about W1 twiddle, one evaluation, to a claim about W2 twiddle at one evaluate. And so eventually you get a claim about WD twiddle, one evaluation of it. Which the verifier computes on its own. That's the whole protocol. Okay. So the point of going layer by layer here is, you're just getting closer and closer to the input. And when you finally get to the input, the verifier knows the input, and in time linear in the input size only, it can check that final claim. Okay.
While we are here, can I have a tiny one, please?
Yes.
Am I correct that the size, the number of gates, the number of how do you say it, the number of things in each layer would be variable without restrictions? I mean that it can grow, then shrink, then grow, then shrink, and so on. Since we uh, since we can have any number of things in the output.
Yes, that works very straightforwardly. Yeah. In fact, the book actually describes things in that level of generality. It might have it makes the notation a little grosser because you have like a different, number of gates in each layer. And so like just denoting the number of gates at layer I, now you just need like a, one letter per layer instead of, but everything works totally fine. No matter how many gates are at each layer, they can all have wildly different number of gates at different layers. Yeah.
Thanks a lot. Thank you.
Yep. All right. Yeah, so that's the protocol. And I think to try to answer the question of like, what would happen if you didn't go layer by layer, I think like the situation would be, you kind of wind up with a claim about, so most of the snarks, what they would do is they would consider a single function like capital W that takes as input you sort of treat the whole circuit as if it's one big layer, right? So like W would take as input the binary label, like the bitwise label of a gate in the whole circuit. So if there are so like 2 to the 30 gates in the circuit means would mean a 30-bit label in the whole circuit, but with this like don't go layer by layer approach, right? And you'd apply some check to this thing, and that will indeed successfully reduce the claim about the original claim about the output gates to a claim about like the multilinear extension of capital W at a random point. Okay, the problem is this W twiddle claim involves the whole circuit. And the verifier only knows the input to the circuit, right? Like it, if it knew the values of all the gates in the circuit, well, then that necessitated evaluating the whole circuit, which the whole point of the protocol was to avoid the verifier doing that on its own. So, the layer by layer approach lets you kind of isolate a claim at the very end about the input alone. Whereas the treat the whole circuit all at once approach leaves you with a claim about the whole circuit. Okay. And without commitments, that kind of claim about the whole circuit is useless. With commitments, it's not really useless. This is how like Spartan works, and implicitly like all the other snarks like Marlin and Planck and all of them also work. But what's happening there is this capital W gets committed in advance, and then this W total of R kind of like just comes out of the commitment scheme. And then the only other thing I'll stop there. So it seems like if you don't want any commitments at all, the verifier needs to know the input and go layer by layer through the circuit. Whereas if you are comfortable with commitments, then what the prover can do is commit to all of the gates in the circuit all at once. And then this W total of R evaluation can more or less just come from the commitment scheme. Those seem to be basically your two options. So hopefully that's a little bit helpful to understand what the design space is. But at any rate, the GKR protocol, no commitments, no cryptography at all, as long as the verifier actually knows the input X to the circuit. Starts with the claim about the output layer, works its way one layer at a time until it winds up with a claim about the input layer. That claim is just one multilinear extension evaluation of the input layer. The verifier can compute that multilinear extension evaluation on its own in linear in the input size time using multilinear Lagrange interpolation. Okay. Questions?
Just to be sure that I'm getting this right, am I correct that this whole GKR protocol is about showing the path from input vector to output vector? Like it's like, look, I know how to get there in the D layers, in the stages, with addition and multiplication. So it will map very nice to R1CS.
Yeah. So R1CS sort of intrinsically, like, so how do I want to say this? The natural transformation of an arithmetic circuit into an equivalent R1CS kind of winds up like flattening the whole circuit into like one giant layer anyway. And so and so you kind of lose this layered structure, and then you're sort of only left with the option of this like treat the whole circuit as one monolithic object all at once sort of thing. So I don't quite know. I guess the answer to your question is like no. Like R1CS kind of throws away the layered structure. I mean, people have also looked at like kind of extensions of layered arithmetic circuits where you sort of replace each layer itself with an R1CS instance. Kind of hybrids between arithmetic circuits and R1CS. Anyway, yeah,
I believe I should hold this question until we see this grand sum, the grand product example.
Yeah, let's do that. Or if
Or
possible, the question is best answered if we cover sort of Spartan or Clover again. We covered Spartan already, but we can either cover Spartan again, or Clover is kind of like Spartan, but for arithmetic circuits. So that might be the best time to answer this question. But maybe the grand product will help. Okay. Any other questions?
Yeah, we have some more questions. So someone new is on stage. KK Star, do you want to ask a question?
Yeah, so I had a question about the polynomial being sum checked. So I think at some point, maybe in the past, you mentioned very often the polynomial being sum checked will be something that's not itself multilinear, but rather like a product of two or maybe three multilinear polynomials. And I think that's the situation like in this case as well in the protocol. So I guess here you have a sum of two polynomials which are which are products of multilinear, which is and you already said that uh, adding polynomials doesn't affect the degree, and so it's still okay. So I guess the question is that is there a more do I have this right? Is it always the case that when you're sum checking, it's going to be the product of two or maybe three multilinears?
Yeah, I think that is right. I mean, there are some, short version is yes. Slightly longer version is there are contexts where it wouldn't quite be the case. So, it's very easy to modify the GKR protocol to not just consider addition and multiplication gates. And so, some people like to do this, and for some applications, and then if you sort of consider like a complicated enough gate, maybe the gate itself can't be represented as just like a product of a few things, and then the sum check would not be getting applied to a product of a few multilinears. But I think those applications are fairly limited. Yeah, I mean, in general, I think a lot of snark design, it'll like basically look up arguments and multiplication gates, will suffice, and like the attention on very expressive constraint systems is kind of overblown. It's like there are limited settings where that can be useful, but it's they're limited. They're not the general case. So short answer is that's exactly right. And so the sum check is getting applied here to So this what polynomial we're applying sum check to. So the polynomial is, I would call it like G of B comma C, where, each of B and C is log number of gates of a given layer. So what is G of B comma C? It's add one twiddle of R0 prime comma B comma C times W2 twiddle of B plus W2 twiddle of C, plus mult twiddle R0 prime BC times W2 twiddle B times W2 twiddle C. And so this is what we're applying sum check to. So R0 prime has been fixed, and so it's sort of no longer a variable. And so the variables in the thing we're applying sum check to are the variables of B and C. And you're exactly right that we have a product of three multilinear things, essentially mult one twiddle W2 twiddle of B and W2 twiddle of C. And so actually what the degree in each variable is 2, right? Because B and C both appear in this thing, but only B appears here and only C appears here. So you have 3 terms, but the degree in each variable winds up being 2. And I think that situation is, in my mind, that's like fully general. Like you can build almost anything you want out of that situation, product of 2 or 3 multilinears. Yeah.
Okay, thanks. So it's just the situation where you have GKR with maybe more complicated gates than addition and multiplication, where you might find the polynomial being sum checked is maybe more complicated.
Yeah, pretty much. And also, like, it's not just GKR, it's general constraint systems, if they have like complicated constraints, that is the only thing that might bring up like something that's not just a straight product of multilinears. And the reason it might not be a straight product of multilinears is because the definition of the constraint involves a polynomial that's not a product of you can represent any polynomial as a product of multilinears just by taking its expression in the standard monomial basis or something. But like people might have constraint systems where like it's pretty gross to write down like the constraints, polynomials in the standard monomial basis, so they don't. That is the situation where you might just never have a product of multilinears in the end. You just have like some moderate degree constraints, whether the degree is 5 or 12 or 20, where no one ever wants to write down the monomials. And so that is the situation where you might not have a product of multilinears coming up.
Thank you.
Yeah, thanks for the question. I feel like I really butchered what's really a quite simple situation.
Question about the check of a circuit, for example, without using the multilinear, let's say, representation of every layer. So maybe I will give an example. Let's say, for example, we have a binary circuit. It's an input. We have an output. So if we want to check the output, okay, the prover must compute the circuit before. So we will check the first output. So he will check that the true in of this output is okay. And after that, he will pick up a random bit. If it is 1, he will pick up the value of the gate of the right. If it is 0, he will pick up the left one. And he will go throughout the circuit until the last one. Before the n-minus layers, he can use, for example, the Schwarzschild lemma. And we will still have, I don't know, I feel like we will still have the Schwarzschild lemma property for the soundness. I don't know if I am correct or I misunderstand something.
Yeah, great. It's a great question. That's exactly the right kind of straw man, alternative approach to have in mind. And that does not work. And so let me explain why it doesn't. And so, yeah, thank you for the question. So just to, so the proposal here is sort of, you just pick a random output gate, right? And then you have the prover provide like the claimed inputs, so let's say this output gate is like a product that products together, these two gates at the preceding layer. So the proposal is have the verifier pick a random output gate, have the prover provide the claimed values of the two inputs to that output gate, and confirm that indeed the product of those two values is the value assigned to that output gate, and then pick a random one of those two gates, and so pick maybe the right one rather than the left one at random, and then just like iterate from there. So have the prover, if that gate is computing like the sum of these two gates, have the prover provide the two inputs to that, and pick the left or right at random and proceed from there. And so this will not pick up on the situation where let's say like exactly one. Here's the easiest attack. Like all of the prover provides correct outputs except for one output, right? So let's say there's 1,000 outputs and the prover provides 999 correct outputs and one output is wrong. Okay, so the probability that the verifier happens to pick the wrong output to check is only 1 over 1,000. Okay, so you could try like boosting that probability, from just 1 over 1,000 to something really, really close to 1. And that would be expensive, but it's like kind of even worse than that, because that situation could arise at each and every layer, right? So, not only do you have to repeat the protocol like 1,000 times, 128 times to get the success probability, for the verifier catching a cheating prover from 1 over 1,000 up to 1 minus 2 to the minus 128 or something. But that's just like, so 1,000 times 128 repetitions just covering one layer. You kind of have to do that for every layer. So what's happening in the GKR protocol is loosely analogous, but the key thing is in the GKR protocol, the verifier kind of winds up checking one value for every layer of the circuit. But here's the key thing. That value is random from the whole field. Okay, so it's not a random gate at that level. So the way you should visualize it is here are the actual gate values, and we index gates with Boolean inputs. So like the length of, the number of actual output gates, we think of, this vector as length, length like number of outputs. Okay. And but what the verifier does is it deals with the multilinear extension of that, right? And the length of the multilinear extension vector is actually field size. So huge. So maybe there are 1,000 outputs, but like the multilinear extension of those outputs, you can evaluate it at any point in the whole field, and there's 2 to the 128 field elements or something. And so the verifier winds up checking not a random gate, but a random value of the multilinear extension, right? Where this is in the whole field. And then you reduce that to a claim about a random value of the multilinear extension of the preceding layer. And then you reduce that to a claim about the random value of the multilinear extension of the preceding layer. So all of these checks are happening outside of the hypercube in the whole field. And so that's bringing in the distance amplifying properties of low degree polynomials, where if even a single gate is wrong in the claimed outputs, like almost everything gets messed up in the multilinear extension, like in the whole field. Does that make some sense? Is that helpful?
Yes, of course. Thank you.
Yeah. Thanks for the question. Yeah. So picking is kind of analogous to picking a random gate and just checking that one random gate was like kind of computed correctly. But random gate really means like random field point, and really it's there R is like in field of the log number of outputs or whatever, right? Anyway, yeah. So you do not have, if the proof relies about one gate, you do not have to get lucky and pick that one gate to check. That one tiny issue gets blown up into something massively detectable out here in the whole field. Yeah. Okay. Other questions?
I had
Yeah, we
I
have
had
a
a quick
bunch.
question also. Is the correct summary of what you just told in the last answer, but thanks for that question, is that the number of output gates is not going to be negligible in the security parameter, which is the field size?
The way I would say it is like the we want to talk about soundness error, but so the soundness error, this is the soundness error, like we want to be negligible in the security parameter. So we want it to be 2 to the minus lambda. Okay. If you do this, like pick a random gate and just check the random gate thing, pick a random gate, right? The soundness error it's actually very close to 1. It's 1 minus 1 over number of outputs. Like that is the probability. So, the verifier only detects the cheating prover if it picks the one messed up output. However, if you pick like a random, evaluation of the MLE of the outputs or the claimed outputs or whatever, the soundness error is like number, or it's really log number of outputs over field size. So rather than this being very close to 1, it's actually very close to 0. Yeah, so that's what's going on. So you think of 1 over field size as being like negligible in the security parameter, and using the MLE multilinear extension and like evaluating that at a random point from the whole field, that's what keeps your soundness error negligible. If you did not move into the whole field, if you did not move out of the hypercube, so you're effectively just checking a random output gate, then your soundness error is actually very close to 1. Your distance from 1 is only like inverse in the number of outputs. Does that make sense?
Yes, sir. So I had a question which connects to the earlier question that the other person asked. Thank you for that. Is that is this the correct understanding that we needs to run in time that is linear in the instance size times the number of outputs of the circuit?
Yeah. So what's happening in the GKR protocol is basically the verifier reads like the public input, like so the real input, the claimed outputs, Okay, and then like one sum check proof per layer, basically. Like that's it. And like really, what's happening here, everywhere it's like some kind of polynomial evaluation. So when I say reads the input, what I really mean is, if the input is X, the verifier, what it really does is it evaluates X twiddle at a random point. Reads the output. What I really mean is it takes the claimed outputs and evaluates the multilinear extension of them at some random point. Right, but these evaluations can be obtained in linear time, so the cost is basically the same as just reading them. And these sum check proofs are like, per layer, it's like log, layer width size.
So am I getting this right, that you're saying that the time linear in instance size is not going to get multiplied by the number of outputs of the circuit?
No, yeah. So it's like the verifier reads the inputs and the claimed outputs, and there's no way to avoid reading them unless they're committed. Because otherwise the verifier doesn't even know what claim the prover is making. And once it reads the claimed inputs and outputs, the only other thing it's doing is checking one sum check proof per layer.
So I'm just trying to understand that this linear dependency on the number of outputs of the circuit is something that is inherent to this particular construction?
Yeah, well, it's inherent in the sense that like what claim is the prover making? The claim is when you evaluate this circuit C, known to both you and me, on this input X, known to both you and me, you get these outputs Y, right? Like, so to even know the claim, the verifier has to know this Y, and that's all. And I'm saying, so you can't avoid the verifier like reading Y. It's part of the prover's claim. And what I'm saying is like that's all the verifier does with the outputs effectively. It reads them. That's it. Like the claimed outputs.
Yes. Thank you, sir. I just wanted to double check. So one last question is that you said that for performing this sum check, the grand product part of that is using the sum check sub protocol is that is the unique. You said that we were able to apply sum check because for every unique gate you have two unique MLEs leading to it.
That is how you keep the prover fast, right? So what's going on? What I'm saying is, okay, like consider for a second. Why don't we consider a circuit where I don't know. There's one like really wide layer, right? And so the sum involved in the general GKR protocol, once you get to that wide layer, it's going to sum over pairs of gates at that layer. So these are B and C, each like binary labels of gates, at a wide layer of the circuit. Okay, and then you have, you're applying sum check to some polynomial in B and C. I won't write it for the 10th time. It's add twiddle of R0, comma B, comma C, but whatever. And this sum is over like number of gates at that wide layer squared. Okay, this is, so if you're very naive, you would look at the sum and you would be like, they're basically like circuit size squared many terms of this sum. Even computing the sum is going to be quadratic in circuit size time. That's a big problem. And so what I was saying is, in fact, you can implement the prover in the sum check protocol applied to compute this big sum without that squared in its runtime. And the reason is, while there are, you're summing over pairs of gates, almost all of the pairs of gates just, for almost all of those pairs B and C, G of B, C is 0. And so if you're get to just have the prover ignore all the 0 terms. So you're summing over a huge number of terms, but only a tiny fraction of them are 0, and it turns out the prover costs only have to grow with the number of non-zeros. Yeah. But and when I will now sort of cover the grand product thing really quickly, because it's pretty simple now that we've seen the general case. And then this sum will not be over quadratically many terms, and then I won't even have to just like make this assertion. It'll just be obvious,
So What I was trying to but thank you for that explanation. What I was trying to ask is, does this uniqueness of two MLEs leading to every distinct gate in the circuit stems out of the fact that each gate is uniquely numbered in the binary representation you had?
Yeah. I mean, that's it.
Okay, cool.
Yeah, and like by definition, every gate in the circuit has exactly two, wires coming into it. So,
So that is the only reason of the uniqueness is what something I wanted to confirm. That's all.
Yeah. It's that.
Okay.
Yeah, that's it.
Thank you.
Yeah. More questions? Okay. All right. So let's see the grand product situation real quickly. So, so here we have an input X to the circuit, and maybe it'll be clearest to draw it as let's say it has, let's say 4 inputs, and we're just going to product them all together. I think it's going to be easiest if we do 8 inputs, just because actually there being 1, so 4, sorry, so let's say 0, 1, 2, 3, 4, 5, 6, 7. That will give us 3 layers of multiplication gates. Okay, and let us just stop 1 layer before. So we have 2 out. So here we go. So a full grand product circuit would just be a complete binary tree, and the output gate would literally be computing the product of everything. Let's stop one gate before the 1 layer before the output. This is just because actually there being exactly 1 output gate is a little bit of an annoying corner case in describing the GKR protocol, that even though it's the simplest situation, it's sort of so simple it kind of becomes a nuisance. So let's say this is our grand product circuit. So just a binary tree of multiplication gates with two outputs. Okay, and so let's say the prover sends the claimed outputs Y, so the claimed values of these two gates here. As usual, the verifier picks a random, R0, and evaluates Y twiddle of R0. And this really is just because there's 2 outputs. This is really 1 random field element. So this is just in field. And now the verifier needs to confirm that Y twiddle of R0 equals W0 twiddle of R0. So again, Y is the claimed outputs, and these are like the real outputs, W0. Okay, and so now I'm going to give a nice simple expression for W0 in terms of twiddle of R0 in terms of W1. Okay, and so this is actually not. So I'm sort of taking the GKR protocol and I'm simplifying it in the context of this specific really nice simple circuit where everything's a multiplication gate and where it has this nice binary tree wiring structure. Okay, so whereas before, the fact, we expressed W0 twiddle of R0 as like a sum over pairs of gates at the preceding layer. Now what we're going to do is the sum will be over, let's say, let's say just a single thing. Maybe I just call it B. So B in 0, 1. And in general, this will be, just B in 0, 1 of W1 twiddle of B comma R0 times W1 twiddle of B comma R1. I'm sorry. Did I? B R0. Yeah. No. Okay. Sorry. Just a complete brain lapse there. Let's fix this. I forgot a factor. That's what was, so sorry. So we're going to have EQ twiddle of R0 comma B times W0 W1 twiddle of B comma 0 times W1 twiddle of B comma 1. Okay. Yeah, sorry about that. This is the right thing. In general, what we have is WI twiddle of let's say of R is the sum over B in gates at layer I, so 0, 1 to the log number of gates at layer I, which I guess would be 2 to the I or something. So I think that's just, let me write it out as I. Log 2 to the I is I. Of EQ twiddle of R comma B times WI plus 1 twiddle of B comma 0 times WI plus 1 twiddle of B comma 1. So let's call this a fact. So that I think it was a mistake to try to specialize the fact to layer 0. I think the general case actually makes clearer what's going on. So this is the fact. Okay, and so let me explain this, and the key point here that makes this so nice. Well, there are two things. So what one is we're not summing over pairs of gates at the preceding layer anymore. There's only like one gate label being summed over here. So that's really nice for making the prover fast, very simply. No longer are you summing over a huge number of terms, almost all of which are 0. You're only summing over a small number of terms. And then the other nice thing is at the end of the sum check protocol to compute this sum, the verifier is going to evaluate WI plus 1 twiddle, not at like 2 completely different points, but rather at 2 closely related points like R prime comma 0 and R prime comma 1. And the fact that these 2 points are so closely related to each other is going to be nice for other reasons. So I'll elaborate on that momentarily. Let's just see the proof real fast. So again, so it helps to have the picture here, I guess. So let me erase this stuff and just bring the fact we're proving up near the picture. Yeah. Sorry for the little writing hiccups here. So WI plus 1 twiddle of B comma 0 times WI plus 1 twiddle of B comma 1. Okay, so here's the proof. So, as always, we have to check 2 things. One is that the right-hand side is multilinear in R. Right. I'm claiming that the left-hand side and the right-hand side are the same polynomial in R. That means we're going to make sure they're both multilinear and that they have the same input-output behavior when R is Boolean. So we want to check right-hand side is multilinear because the left-hand side is by definition, it's the multilinear extension of layer I. And that when R is Boolean, they have the same value. WI twiddle of R equals the right-hand side of R. Okay, and so the right-hand side is clearly multilinear in R because R is only getting fed into EQ twiddle. Remember, this is the multilinear extension of the equality function where, if R and B are both Boolean, it's just spitting out 1 if they're equal and 0 otherwise. So this equality function is product over each coordinate. J equals 0 to I minus 1 of Ri times Bi plus 1 minus Ri times 1 minus Bi. Just checking equality coordinate by coordinate of R and B if they're over the hypercube. And so R is only getting fed into EQ twiddle. EQ twiddle is multilinear, so the right-hand side is clearly multilinear. It's a sum of a bunch of multilinear things. It's multilinear. And so now let's consider the case where R is Boolean. Well, this is going to kill every B. This EQ twiddle thing kills every B except the B that equals R. And in the case that B equals R, what we have here is WI plus 1 of R comma 0 plus WI plus 1, times WI plus 1 of R comma 1. And that's exactly what a binary tree of multiplication gates is doing, right? Like the label of label of this gate at layer I here is 0, and its two in neighbors are 0, 0, and 0, 1 at the preceding layer. And the label of this gate is 1, and its two in neighbors are 1, 0, and 1, 1. So, what's going on here is for any, gate R at a given layer, that gate computes the product of the two gates at the preceding layer of the form R comma 0 and R comma 1. And so that's all I've written here. That's it. Okay. And so great. I mean, that's it. So the right-hand side is multilinear in R. And when R is actually a gate label, when R is actually Boolean, the right-hand side does the right thing. It equals, Wi plus 1 of R comma 0 plus Wi plus 1 of R comma 1. That's a binary tree of multiplication gates. Okay. And so the GKR protocol applied to this thing will just apply, at each layer I, the verifier, sort of starts with the claim Wi total of R equals something. And to check that claim, it just applies sum check to compute the sum. Again, at the end of sum check, the verifier needs to evaluate the polynomial being summed at a random point. So it needs EQ twiddle of R comma R prime, times Wi plus 1 twiddle of R prime comma 0 times Wi plus 1 twiddle of R prime comma 1. Now this the verifier can get in log time, right? I wrote this expression up here. So this can be obtained in I field malts or something. Where I, at the beginning of the protocol, I is like 1 or 2 or 3. And then at the end, it's still only like log, circuit size. And then here we get to, this issue I brushed under the rug before, of we really want the verifier to be left with evaluating Wi plus 1 twiddle at a single point, but it has to evaluate Wi plus 1 twiddle at 2 points, R prime comma 0 and R prime comma 1. Okay. And so how do we reduce those two evaluations to one? And it's very simple. But we effectively just take a random linear combination of the two claims. But another way to describe it is sort of pictorially. We can write, like there R prime comma 0 and R prime comma 1 like live on a line. And so here maybe I don't want the picture. Maybe that's overkill here since these 2 points are sort of related. So consider the line in field to the I plus 1, which is t maps to R prime comma t. Okay, so this means like if you look at this line, call this like L of t is R prime comma t. L of 0 is R prime comma 0, and L of 1 is R prime comma 1. So this line, so the picture which I was starting to draw is like if I draw you this line in I plus 1 dimensional space, if I 2 point R prime comma 0 is on this line, and so is R prime comma 1. And so what we can do is we can have the prover send I feel like this is gross overkill, and everything is actually much simpler than I'm about to write. But what the prover can send Wi plus 1 twiddle restricted to L, send, let's call it R of t, not R, another letter. Let's call it S of t equal to Wi plus 1 twiddle of R prime comma t. Okay, and now this is a line. This is so I shouldn't. I'm confusing people by forget this line. Forget what I wrote up here. We're just going to have the prover send Wi plus 1 twiddle, which is this is a multilinear polynomial in I plus 1 variables, but we're just going to fix the first I variables to R prime and only leave the last variable kind of as a variable. Okay. Now, because WI plus one twiddle is multilinear, if I sort of fix all of the variables being fed to WI plus one twiddle except the last one, what comes out is literally like a one variate line. So this is like, A times T plus B, right? Literally the prover is just sending A and B. Okay. And so what the verifier is going to do is verifier understands, S of 0 as the prover's claim for WI plus one twiddle of R prime of 0, and S of 1 as the prover's claim as to the value of WI plus one twiddle of R prime comma 1. These were the two evaluations of WI plus 1 that the sum check verifier needed. So here the prover is sort of giving them to the verifier via S. And then what the verifier will do is just pick, like T at random from the field, and trust, it's safe, to believe, like S of 0 indeed equals WI plus one twiddle of R prime comma 0, and S of 1 equals, WI plus one twiddle of R prime comma 1, so long as the verifier, is convinced that, WI plus one twiddle of R prime comma T equals S of T. Okay. So I mean, pictorially, it's like we're taking, WI plus one twiddle, has many variables. It has like I plus one variables, but we only care about its values here, at these 2 points. And these 2 points both lie on like a very simple line. Yeah. And this line is obtained by fixing all but the last variable. And so we're just asking the prover to send WI plus one twiddle's values at all points on the line. And because WI plus one twiddle is so simple, it's multilinear. When you only care about his values on this nice line, it actually just those values are themselves given by a line. So we sort of, it's like we ask the prover to send WI plus one twiddle restricted to this line. That itself produces a line. And then we're just picking like a random point on the lines and like making sure everything works out at that one point. So that's one view of things. I took this view because it's the view I use when I present the general case as well. But I think it's probably overly complicated, and like all we're really doing here is taking a random linear combination of the two claims and kind of believing that both claims are correct. One about R prime comma 0, one about R prime comma 1, if and only if the random linear combination of the two is correct. And so because R prime comma T is sort of like just a random linear combination of R prime comma 0 and R prime comma 1. So anyway, all right. So that wasn't the best presentation, but you get the idea. So in summary, like you can kind of, people just call this the GKR protocol for grand products. I'm maybe underselling, some credit to some old paper of mine a little bit, because, what we apply sum check to is different. Of course, it really is just looking at what's kind of really going on in the GKR protocol and simplifying it, changing the polynomials when the circuit is this very simple special thing. But the simplification does have some really nice implications, whereby the sum being computed in each round is over a small number of terms. So it makes it really easy to make the sum check prover fast. And then the two evaluation points of, that the verifier needs, for the gate values at each layer are so related and simple that it's like really, really easy to reduce those 2 points to 1. Okay, so that is the content I wanted to cover today. I can stick around for questions, but if I've taken too much time, feel free to drop. Thanks so much for your patience.
Awesome, thanks. I had one question from chat that I wanted to try to propagate. So there's kind of confusion around what is considered, I guess, in terms of when we're talking about zero knowledge. It seems really important to define what the witness is, since that's the thing that we're trying to not reveal. And it seems like in this case, the inputs are not considered part of the witness, and they're just like, how does that kind of get defined? Like, who gets to decide what is part of the witness or not in the context where we have this input?
Yeah, so zero knowledge almost doesn't make any sense if the verifier knows the input and just wants to make sure the prover evaluated some small circuit on the input, right? Yeah, so basically, because that problem, if the circuit is is polynomial size, if the circuit's not ridiculously big, then the verifier on its own can solve the problem, and so there's nothing to hide. There's nothing to hide from the verifier. The protocol's point is just to save the verifier some work, and there's no private anywhere. Yeah.
So in these cases, we're never actually giving the verifier the full input. Is this kind of where we go back to the commitment idea?
Exactly. So what will really, but then even in that setting, it can be a little bit annoying to talk about the quote witness. There's sort of two people will talk about an extended witness or and what's really going on is the following, in the ZK in the privacy relevant application, the prover will be claiming to know some secret value, some secret string that we call the witness for that application. Maybe it's like a secret key controlling some Ethereum wallet or something, right? And so that will be called the witness, and that is what ZK is meant to protect. Okay, but then the way the snark tends to work is you sort of turn, like the prover will be claiming, I know, I know a witness satisfying some property. So what you do is like you write a computer program that takes as input the claimed witness and confirms it satisfies the claimed property, right? Then you turn that computer program into a circuit. Then you
and now your witness is something bigger, right? Like now your witness to the circuit is actually the like execution trace of the computer program, so it's much bigger than the original thing we were trying to hide.
Exactly, typically, yeah. Because if and this is where if you don't have the circuit take like what we call advice inputs, untrusted advice inputs, the circuit will often be huge, right? So as a result, the circuit satisfiability instance, the witness to the circuit is much bigger than the witness you started with, because of all these extra untrusted advice inputs that are there to kind of keep the circuit small. However, the ZK snark for circuit sat that you then want to use should treat the extended witness all as private data, because the untrusted advice inputs may well, each and every one of them may well depend on the original witness you started with. And so, anyway, so in the end-to-end application, like the private data that ZK is meant to protect is really that original witness you started with. But in order to protect that, it actually is typically necessary to also protect the entire extended witness, a lot of which is just untrusted advice inputs that were not there in the original witness. Because if I told you an untrusted advice input, that may well give you a little bit of information about the original witness. Is that helpful?
Mm-hmm. Yeah, that was a great explanation.
And then to be clear, like the GKR protocol in that setting would not be ZK directly, because these messages in the sumcheck protocol, while they are not
the intermediate.
The intermediate ones, like all of that, it's like, they're complicated functions of the input to the circuit, which, in general, it has been committed and is private and can't be leaked in any way. So they're very weird information about that secret private input, but it still is information about that secret private input. And so if you just say run the GKR protocol, on this committed input, and then at the end, reveal only the information needed, by the GKR protocol about the committed input, which is just one multilinear extension evaluation, like that is not ZK. It's like the information that's potentially getting leaked about that committed, secret input is very weird, and it's hard to see how anybody would use that to like.
But it is information. It does like narrow down what the possible inputs are, right?
Yeah. And so what you would actually do if you cared about ZK, there are ways to take to the sum check protocol and like blind or mask the prover's messages in it so that they're effectively just like random garbage. And yet you somehow still don't give up soundness. Or what you could do is take this non-zero knowledge, protocol, rendered non-interactive with fiat Shamir, and then give a ZK proof, the non-ZK proof. And so these are the two standard ways of getting zero knowledge. You either kind of do it directly by, doing some obnoxious, modification of the non-ZK thing so everything's masked or blinded or whatever, or you just do composition with the ZK thing so you effectively ZK prove the non-ZK proof. But both of those techniques apply, with GKR based snarks as they do to like Planck and Marlin and Gross 16 and stuff as well.
Professor, I had two quick questions. So one might be very traditional, archaic, interactive proof theory, but the statement that zero knowledge does not make any sense when the verifier knows instance really throws me off. So what exactly is the basis of that particular claim that was just made?
Yeah,
it was input, not instance. I think that might be the main distinction. Like I think when we say instance, to me that means like the circuit, but the input is the actual witness that we are trying to hide. Like we're trying to show that we know the witness, but not reveal it. And so we don't want to show the input. We do show the instance.
So what I would say, the GKR protocol, normally the prover and verifier both agree on the circuit as well. Because if the verifier didn't know the circuit in some way, then the prover's claim doesn't make any sense, right? The claim is I evaluated this circuit on this input and it produced this output, and so if you don't know the circuit and the input, there's just it's not a well-defined claim. So maybe that, but what's going on is key here was that the circuit is like small and you only care about one input to it, right? So here are other related settings where ZK does make sense. Okay, so one setting would be circuit satisfiability, right, where the claim is there is a satisfying assignment to this circuit, or I know a satisfying assignment to this circuit. Okay, and then how do I want to put this? Either the verifier itself doesn't know the satisfying assignment, and then it makes sense to treat that as I guess that's how I want to say it. In that situation, the verifier itself doesn't know the satisfying assignment. We think it's computationally intractable for the verifier to find that assignment on its own, because circuit stat is an intractable problem. It's NP-hard problem. And so it makes sense to treat that satisfying assignment as secret information that the verifier doesn't know. And thus, to talk about the proof not leaking any information about that satisfying assignment. So that in that case, the prover is basically claiming to know an X such that C of X equals 1 or something. And the verifier doesn't know X, and so X is secret. All right. Another situation could be where the verifier knows X, but let me leave it at that. That would be like the main setting where zero knowledge would make sense. So again, the difference is there, the verifier doesn't know. Okay, so does that make you no longer feel weird about it?
Yes, sir, it does. I mean, I thank you. I appreciate the extra effort that you had to take to answer that. Thank you, sir. The other question I had, and this might be very naive, I wanted to know that the verifier choosing this coefficient of the random linear combination for the last step where you're compressing the last two evaluations into one evaluation. So this increases the round by 1. I just wanted to double check that is the thing.
Yes. It does. Yeah. So rather than there being, so you'll run sum check once per layer. That will have, log for layer I, that will have like I rounds or something for the grand product circuit anyway. And then this will be one more round on top of that before moving to the preceding layer. Yeah.
Okay, thank you, sir.
Hello, can you hear me?
Yep.
I might be foreshadowing something, but let's say we had like two, or let's say we had two vectors and we want to check that they permutations of each other.
Mhm.
Would we have two circuits, binary tree circuits for that, or just one?
Yeah. So what would happen? This is how you would do it. So the so let's call the vectors a and b. Let's say a0 to an minus 1, b0 to bn minus 1. Okay, so what we would do is the verifier would pick a field element at random and check that the product over all entries of A of R minus that entry equals the product of same thing, but with A replaced by B. And so this would be, basically, yeah. So if A and B are permutations of each other, this equality will always hold no matter the choice of R. And if A and B are not permutations of each other, it's very unlikely that this equality will hold as long as, the field size is much bigger than N. And so the question now is like, how do you compute these two big products? And the answer is you would apply the grand product argument, kind of twice, if you will, to, two vectors. The vectors are not literally A and B. It's, like I'll call it A prime and B prime, where A prime, ith entry is R minus AI, and B prime ith entry is R minus BI. And yeah, and there's a bunch of little twists you could do here. So at the end of, yeah, I don't know. So you could just have the prover like send the two, claim product values and, apply GKR sort of totally independently to each, or, I think it probably makes more sense to consider the circuit. It's actually fairly convenient that I stopped the grand product circuit in my example like one step below the output, because that's exactly what actually makes a lot of sense here. So you would treat it as one big circuit. So that just stops, so you just cut off this last gate at, at the output. So it's one big circuit with two outputs. And so you would apply the grand product argument, that I just described to this one big circuit, and at the end of the GKR protocol, the verifier. Let's call A prime followed by B prime. Let's call that C. So the verifier needs to evaluate C twiddle at a random point. Say I don't know, R arrow. This would be in field to the log n, 1 plus log n or something. And it turns out that that this can be, this has a simple expression, which I'm not going to try to figure out right now, but it's not that complicated. In terms of one evaluation of A twiddle and one evaluation of B twiddle. So let me not work it out, but basically because A prime and B prime are such simple expressions of A and B, I guess I erased what they were, but remember A prime of I was R minus AI and B prime of I was R minus BI. Because they're such simple expressions of A and B, this is like this evaluation that you need is like a trivial combination of one evaluation of A twiddle and one evaluation of B twiddle. That's what the whole protocol would look like end to end. Does that answer the question?
Awesome, thanks.
Yeah, great question, by the way. Yeah. More questions?
This is our last one.
Can you hear me?
Yep.
Great. Couple of times you said that prover and verifier shares share the information about the circuit, but I'm having a hard time to see where do they use it in the description of the protocol.
Great. Yeah. So it's used in. So in general, the description of the circuit is entirely encompassed by the add twiddle of I and mod twiddle of I for each layer. And so remember, so what's going on is in general, the GKR verifier for each layer is just going to need one evaluation of each of both of these polynomials. Okay. And this I like really brushed under the rug, but for circuits with like zero repeated structure where like every gate is like completely like the wires, the inputs of that gate, are completely unrelated to what are the inputs of all the other gates. These evaluations might take time linear in the size of the circuit. And that's like annoying that's like a pretty slow verifier. The verifier in principle is not saving any time then compared to just evaluating the circuit directly on its own. But like most circuits that arise in practice have some kind of repeated structure. They do the same relatively simple thing over and over again. And in those contexts, like evaluating add-I twiddle and multi-twiddle at one point, you'll be able to do that really quickly, like much faster than evaluating the circuit, gate by gate on the verifier's own. In the grand product, the special case of the grand product. Remember what we applied sum check to. The verifier, wanted WI twiddle at some point, and so it applied sum check to compute, sum over B of EQ twiddle of R comma B times WI plus one twiddle of B comma 0 times WI plus one twiddle of B comma 1. And so, the fact, and so like, this EQ twiddle thing is sort of kind of capturing the fact that we're interested in a grand product here, that the input to, to a given gate at a given layer, gate A at this layer is A comma 0 and A comma 1 at the preceding layer. That's why EQ twiddle is coming up here. So that is maybe a cleaner, more concrete way to see in a special case, like where is the circuit itself coming into the protocol. Basically the polynomial sum check gets applied to. That polynomial somehow captures the wires at the appropriate layer of the circuit. Does that make sense?
So it's kind of question of pre-processing or compiling the whole thing before evaluation.
Yeah, pretty much. So like if you just want to handle like totally general circuits with no repeated structure, typically what will happen, and you're not happy with like a linear time verifier. In some cases, linear time verifier might be okay. The proof will still be short or whatever. The verifier is just spending a ton of time, evaluating add twiddle and mul twiddle at a point. If you're not happy with the verifier spending all that time and your circuit doesn't have repeated structure at all, which again, I think is like really never the case, but what people will do is basically have an honest party commit to add twiddle and mul twiddle in pre-processing. And that way the untrusted prover can provide the necessary evaluations that the GKR verifier needs of these polynomials, kind of online, and prove that the provided evaluations are indeed consistent with the commitment. So that would be where pre-processing would be coming in. If you're having an honest party in pre-processing commit to these things so that the verifier just doesn't have to deal with them itself in the online phase. Does that make sense?
Yeah, that's a lot of color to the thing. Thank you.
Yeah, thanks for the question. Okay, so I hope that today was informative and the various tough parts weren't too bad. So thanks as always for sticking around till the end. And yeah, we'll go to I'll talk to Abby. We'll get a poll together or something for feedback on what to discuss next. And yeah, hope the GKR protocol was interesting. It's really a beautiful protocol, and I'm trying to kind of spread its gospel out there. So you're the great guinea pigs. And
Nice.
yeah, I will take more
Sounds good.
questions.
So that's all the questions. I think we're good, and we are on for next week.
Great.
Cool.
Talk to y'all soon.
Thanks. Bye.